Okay, AP scholars, let's finish off Unit 4, Section 9, Redox Reactions. We introduced the idea already a couple of sections ago, so let's get a deeper dive going now. So here's a reaction that we've done in lab where we take some copper, stick it in a solution of silver nitrate. Over time, it turns into this bluish solution, which is copper 2 nitrate, and the wire starts growing this winter fur coat that's actually silver. Okay. When we look at this reaction, okay, we see that this is a free element, so we know its oxidation number 0. We know this is an ionic compound, and since there's 2 nitrates, that means this is +2. So copper is going from 0 to +2. On the other side, we had started with silver nitrate over here, so if nitrate's -1, silver is +1. But over here, it's a free element, it's 0. So silver is going from +1 to 0. So we know that if the oxidation number is going up, it's losing electrons, which means it is being oxidized. So copper is oxidized. We know that if a substance oxidation number goes down or is reduced, the substance is gaining electrons, and that's reduction. So we know silver is being reduced. Okay. All right, now, why did we say in theory in the last thing? Well, not everything can replace everything else, okay? Different chemicals have strengths to them, okay, based on their electronegativity, their size, their ionization energy, and so on. There's a way that reactions can happen, and some things don't happen, okay? When we get into the idea of spontaneity and all that later on, then we'll come back to that as well, okay? When we talk about redox reactions, most redox reactions, not all, but most redox reactions are not reversible. Okay? So, I shouldn't say that, are not spontaneously reversible. They would not happen on their own. We could force them to happen, but they will not happen on their own. So we have to have a means of identifying which ones will and which ones won't. And so we looked at something called an activity series. Now, the activity series you looked at in the previous chem experience is probably different than this one by a bit. This is the one that they used to provide in the AP packet. Now they only give it when needed, so it's not there all the time. But in this packet, if you notice up at the top, it's saying something about standard reduction potentials. Okay, don't worry about what potential is yet. That whole number thing on the side is way, way, way later in the end of the year. Okay. But let's look at all these reactions. Notice that in all these reactions, at least one electron, or more than one electron, is a reactant. They're all talking about gaining electrons. All of these reactions are reduction reactions. That's why they're reduction potentials, okay? So if we're talking about metals, and metals like to oxidize, you notice that the metals are at the bottom of the list. So really, when we talk about oxidation, we have to look at this list in reverse. Okay, so there's no question that fluorine is the best at being reduced, okay, but lithium is the best at being oxidized, okay, and believe me, this is not something that you could easily memorize because you would think, all right, well, if lithium is first, then what's next, sodium or beryllium? No, cesium. Oh, okay, you know, and then potassium. And, you know, sodium doesn't come for a little bit down the line there. So it does not make as much sense without knowing a lot more chemistry. Okay, so this is just reference. This is never something you would be asked to remember. Okay, so when we talk about redox reaction to happen, like that last one, okay, we have to make sure that the element that is better at being reduced is the one being reduced, and the one that is better at being oxidized is the one that's being oxidized, okay? So, for example, you know, if we look for, let me pull it up here. If we look back at our reaction, okay, here's the copper going from 0 to +2 that we talked about, and here's the silver going from +1 to 0 that we talked about. We see that silver is higher on the list. Silver is better at being reduced. Well, that's what we said silver was going to do. Copper is being oxidized. That's what we said copper is going to do. So that makes sense. There's no problem there. But if we looked at the reverse reaction, right, Now in the reverse reaction, we're starting with copper as +2, ending with a 0, so copper should be reduced, but copper is not better at being reduced than silver, so this reaction is not possible. Okay, so there again, we're going to see that reactions have a way to go, not reversible when we talk about redox. Okay, and yes, there are some exceptions, but not in single replacement reactions, and that's where our focus is going to be. All right, so again, this chart is just a means of reading off for strengths. Okay, the higher up it is, the better it is at being reduced. The lower it is, the better it is at being oxidized. Okay, so let's use that to talk about another example. Okay, I'm sorry, no, that's the same example. Never mind. Oh, balancing half cells. Wow, lost my train of thought. Okay, so I haven't used the term half cell yet. I guess that should be where we start, really. You'll notice that, again, these reactions show the electrons, but they're only showing one element, okay? That's what makes it a half cell. These are just reduction reactions, okay? And if I turn this around and look at these reactions from right to left, then they're oxidation reactions. So we see that copper is being oxidized, so I take this reaction and I reverse it. And I see that silver is being reduced, so I just copy that reaction down. But when I go to put them together, because two halves make a whole, right? If I want to look at the whole cell or the whole reaction, I need to make sure that the electrons are balanced. So if there's 2 electrons being transferred by copper and 1 by silver, that's a problem. The law of conservation of matter would have a problem with how can something give off 2 electrons but something else only take on 1? We're losing electrons. Electrons are matter. No bueno. Okay? So what we have to recognize is that they have to be balanced. So we just make sure we balance by doubling one of the half cells, in this case, the silver one, to 2, 2, and 2, because now that'll have 2 electrons coming out, 2 electrons going in, and we're good to go. So when we balance this, when we add up these 2 reactions, the electrons will cancel out because I have 2 and 2, okay? And now I'm left with copper plus 2 silver ions yields copper 2 ions plus 2 silvers, okay? So it brings us right to the net ionic equation. And again, you don't have to write in phases. I don't know why I did one case and not the rest of them. Okay? Phases do not have to be written in unless specified. Okay, so what if solid zinc is placed in a solution of nickel 2 chloride? Will a reaction happen? And if so, what is the net ionic equation? Okay? So take a moment, look at the chart there on the right, and decide if the reaction will happen, and then figure out the net ionic. I'm going to go on. Okay. So in terms of will it happen, I look for zinc, I look for nickel. Zinc is the one that's trying to be oxidized. It's going from 0 up to +2. Zinc is lower on the chart. Yes, this reaction will happen. Okay. All right. So now in terms of balancing or figuring out the net ionic, I just copy down my half cells. So I have, remember the oxidation one has to be reversed. So I say zinc yields a zinc 2 ion plus 2 electrons. And for the nickel, since it's being reduced, we leave it exactly as it is. Nickel 2 ion plus 2 electrons yields nickel. I see that I have 2 electrons in each. They're going to cancel out. And so I'm going to be left with this as my net ionic equation. And please, please, please be careful. Again, people always will cancel out and say, well, zinc cancels out with zinc, nickel cancels out with nickel. No. Only spectator ions can cancel out. This is not an ion. This is not an ion. There's no way they can cancel out. Okay? So only spectator ions cancel out when we're doing these. All right? So now let's think about this one. If liquid bromine is placed in a solution of aluminum chloride, will a reaction happen? If so, what is the net ionic equation? All right, give it a try. I'm going to go on. So now we're working up here. We're comparing chlorides and bromides. Okay, so we know we're starting with liquid bromine, adding it to aluminum chloride. So the bromine should replace the chlorine in theory. So we get chlorine out, aluminum bromide. So bromine is going from 0 to -1. Bromine is being reduced. Chlorine is going from -1 to 0. Chlorine is being oxidized. Except that chlorine is higher on the list, so chlorine is the one that should be reduced, and bromine is the one that should be oxidized. So this is no reaction. Okay? It will not happen, period. Well, unless we force it to. Alright, so let's go over that balancing of half cells. Just throw out a couple quick ones. Okay, so balance these two half cells. So on the right, we have an iron oxidation half cell and a tin 4 reduction half cell. And on the right, we have a fluorine reduction half cell and a gold oxidation half cell. Alright, so in the first case, our least common multiple would be 12, so I have to multiply the iron half cell by 4. I multiply the tin half cell by 3, that gives me 12 electrons in each. So the net ionic should be 4 irons plus 3 tin 4 ions, yields 4 iron 3 ions plus 3 tins. Alright, what about over here? Well, we have 2 electrons and 3, so the least common multiple is 6. So I'm going to multiply the fluorine half cell by 3 and the gold half cell by 2, so that gives me 6 electrons in each. And now when I add that up, which, why didn't I add that up? I don't know. I really don't know. I just don't know. Alright, anyway, we would end up with 3 F. Alright, that's not working for me. We're going to do that. 3 F 2 plus 2AU. And that's not working for me either. Ow. I'm going all out on this video. Yeah. Come on. Working. Yields 6. 2AU 3 plus. Okay. Yeah. And notice, by the way, whenever you're looking at net ionic equations, the total charge on both sides should be the same. So for example, on this one, the total charge is 0, and 3 times 4 is 12. On this side, 4 times 3 is 12 plus 0, so it's 12 and 12. Whereas here it's 0 on this side, and negative 6 and positive 6, so 0 on this side. Okay, so if you're not getting a total charge equal on both sides, you're definitely making a mistake. Alright, so now we got to talk about the term agents real quick. So looking at that reaction that we've seen before, we see that zinc is being oxidized, nickel is being reduced. Okay? So what is an agent? The term agent is short for reagent, which is an older form of the word reactant. Okay, so agents have to be reactants. Have to. Okay? That means they have to be on the left side of the equation. Have to. Okay? The oxidizing agent is a chemical that's going to cause oxidation to occur. It's not the one being oxidized. It's causing oxidation to occur. So logically, if zinc is being oxidized, which reactant caused the zinc to oxidize? Well, that was the nickel. Specifically the nickel 2 ions. Okay? Or nickel 2 chloride, depending on what we were told that we had. Okay? The reducing agent is a thing that causes something else to reduce. It is not reduced, it causes it. So if nickel is being reduced, what caused it to reduce? Zinc. Okay? So the term kind of goes almost opposite of what's going on. Zinc was oxidized. Zinc is the reducing agent. Nickel was reduced. Nickel 2 is the reducing, oxidizing agent. Okay? So they are always going to kind of work like that. Alright, so let's take a look at these two reactions. I think I need to move my face out of the way there a little bit. Alright, so what's going on here? What's oxidized, what's reduced? What's the oxidizing agent, what's the reducing agent? Okay, give it a try. I'm going to go on. Alright, so copper is oxidized, silver is reduced. That means that the silver ions, we got to be specific, is the oxidizing agent, and the solid copper is the reducing agent. Okay? In this reaction, bromine is oxidized, fluorine is reduced, which means that the F2 gas, and again, phases don't have to be there on that, very random with phases, is the oxidizing agent, okay? And bromide, Br negative, is reducing agent. If you tell me it's a reducing or oxidizing agent, and it's not the way it's written here, it's wrong, okay? It has to be a reactant. It has to be what would go into the left side of the equation. So if we go back to talking about this table again real quick, okay, we said that fluorine is the best at being reduced. So that means it's the best oxidizing agent. We said that lithium is the best at being oxidized, okay, that means that it is the best reducing agent. So we could look at this table in terms of oxidizing agents or reducing agents as well, okay? If we talk about them in terms of oxidizing agents, then clearly fluorine is the best oxidizing agent and lithium is the worst. If we talk about it in terms of reducing agents, lithium is the best, fluorine is the worst. Okay, so let's look at these and talk about, first of all, putting these in order of increasing strength of oxidizing agents. Okay, so list them in terms of oxidizing agents and then list these in terms of reducing agents. Now keep in mind, you know, when you flip the table around, you're really looking at it almost like, you know, completely turned around, because that's going to be a factor in this. Okay, all right, I'm going to go on now. All right, so I put some dots next to these reactions. Okay, so down here, let me zoom a little bit. Okay, we see the water reaction down here. Then we have the chromium 3. Then up here is the copper 2. Now you could argue one or the other reaction. I was really leaning more towards this one, but either way. Then we have oxygen. Then we have chlorine. Okay, so this table, again, the higher up is the better it is at being reduced or being an oxidizing agent. Okay, so that means then we got to look at it the reverse way. Notice I put the dots on this side now, because when we flip it around, when we talk about reducing agents, we're talking about things being oxidized, so that means we have to look at the reactions from right to left, okay? So we're starting at the top and working our way down, so the water, again, is the weakest one out of the set. Then we find the iodide, then we find the tin, then we find the zinc, and then we find the aluminum, okay? So there are our answers. I hope that makes sense. We'll spend a little class time going through this more yet, but that's the notes at least to get you going. All right, have a good one, guys.